Okay, so we're going to jump in here, starting with the most difficult problem of the test, at least of the ones that I kept. So this is a writing program, and we're comparing it to a traditional program. We're looking at an outcome of writing achievement. And we're trying to find these variables, moderating, extraneous, confounding, and I'll explain a little bit more there. So the independent variable here is the variable that we are changing. So we're looking at a comparison between them. In this case, it's the type of writing program. So we're comparing the new one and the traditional. This is our independent variable. This is what we're really interested in, which one has the bigger effect. The outcome that we're looking at, our dependent variable, is writing achievement. So writing achievement is what we're measuring as an outcome. So our independent and dependent variables are always going to be important ones that we want to keep. That's the focus of the study. However, in most study, there's these other variables that kind of get in the way. Gender could be extraneous or a confounding variable in a typical study like this. But notice that it says the study is conducted using a sample of only female. In other words, there are no males in this study. So because of that, gender is not going to influence our results at all. We are only concentrating on females, so we don't have to worry about this idea of being two separate populations that maybe have different results on this outcome. Now the grade level is an issue. So it tells us that the students are from 4th, 5th, and 6th grade. So we know that there could be very different, it could be different, the effects of the program on the outcome based on how high up you are in elementary school. So certainly that could skew the results a bit. Now, the reason it says a possible moderating variable, a very appropriate way to handle that would be to split the sample into grade 4 and then do an experiment there, grade 5 do an experiment there, and grade 6 do an experiment there. If you did that, then you'd have even more information because you could look for maybe it's effective at a certain grade level or not at another, which is, by the way, called an interaction. If we don't take that into account, it's potentially going to affect our results. It's going to potentially give us an outcome that is more or less effective than what the real outcome could be more or less effective than what we see it as a result, because we could be getting some influence from the grade level, even though we're really trying to focus on the type of writing program as our independent. Okay, let's go on to the next one. Okay, p-value. So this is something I think a lot of people hated after taking this test, but at the same time, it's very, very important. So p-value is the probability of the observed outcome if the null hypothesis were true. Now, why? Let's just take a look at the most popular answers. Probability that the null hypothesis is true. We never know with what probability the null hypothesis is true. It's crazy, and it's something that's very controversial in statistics, but we never know really the probability of the null hypothesis being true. What we know is, if the null hypothesis is true, then we can set up all kinds of statistical distributions because we use the mean of the null hypothesis as our mean of our distribution, and so we can say this. Now, I guess the second answer here, for the same reason, we never know if the null hypothesis is false, because if we knew one of these, then we would know the other also. Okay, and this is more just a definition of what p-value is. Okay, to interpret a correlation of negative 0.3, so correlation is your R value, but variation, percent of variation explained, is your R squared. So if we have negative 0.3 squared, that would give us 0.09, which is 9% of variation. What does that mean? It means if we have two variables, say, let's say ability to read, verbal ability, reading ability, and math ability, maybe there's some connection. Maybe there's it would be a positive zero point 0.3, I would assume here. Um, but when we square that to get 9%, what that would say is 9% of the differences that people have in their math ability can be somehow associated with what their verbal ability is. Or if you tell me someone's verbal ability, I can know with about 10%, I know about 10% can explain the variation in their math ability. Now, the higher that R squared is, the more closely the two are related. So, main point there, to get percent variation, you square the R. Now, this isn't a cause, this is just a correlation. We're not saying that math ability causes 9% of verbal ability or vice versa. Okay, this was one question that several of you pointed out as being frustrating, although I will say that this is a very good question and it's worded very carefully, not trickily. So when I say that a reliable measure measures whatever it measures with consistency, what that means is it could be totally measuring the wrong thing. Let me restate that. A reliable measure can completely measure something it's not supposed to. It could be created to measure math anxiety, and really, maybe it doesn't measure math anxiety at all, but maybe it measures, I don't know, ability, swimming ability, or something completely different. But as long as it consistently produces the same results, no matter how many times you take the test or whatever it is, then it's a reliable measure. So reliable means consistent. It doesn't mean that it's measuring what it should measure. This is the definition of validity. So this popular answer here, that would be a measure that's both valid and reliable, which is what we want, of course. But I want you to know the difference between those two because it is very important. Just because a test is reliable, just because you see some report in the news that some test is very reliable, does not mean that it's accurate or valid. Okay, so this point is also getting in this concept of significance level and p-value. Basically, what is happening here is the null hypothesis is true. This is just another way of saying that the null hypothesis is true. The population we're sampling from is the same as our sample, basically. Or sorry, the population we're sampling from is the target population we're interested in. All this to say, null hypothesis is true. This level of significance is something the researcher chooses. It's not dependent on what the outcome of the test is. What you are saying is, this is the percent that I'm willing to take for type 1 error. This is the percent of the time that if I do reject something, I realize that it's going to be false if the null hypothesis is true. In other words, you're assuming that there will be sometimes when you make a mistake, and you get to choose how often it is. Now, if that's true, why wouldn't you just set level significance at 0.01 and only make a mistake 1% of the time? Because the lower your chance of type 1 error, the higher your chance of type 2 error. A common example is in criminal courts. A judge has to decide based on the evidence whether to let the prisoner go or convict him and say you're guilty. Now, if the judge would just say that everyone is guilty, he would catch every criminal that came into his court. There'd be no chance of the criminals deceiving him. But the problem would be he would lock up a lot of innocent people. Similarly, if he just let everyone go, he wouldn't lock up innocent people, but he'd let a lot of criminals go. And so that balance between choosing where exactly do we want to draw the line is typically set at 0.05, but whatever it is, it's the level of significance, and this kind of gives a definition for what it is. So 5% of the time, we would reject the null. Okay, statistically significant is that the difference in population are not likely due to chance. So some people said all of the above are correct, and this differences are meaningfully large. This is very, very important because this is one of the common misperceptions in the general public. Statistically significant means nothing more than there is some kind of effect, but the effect could be tiny, tiny, tiny. Maybe this one pill raises your IQ by 0.00001. That really is meaningless, and it's certainly not worth paying $10 for a bottle of pills or something. So in making decisions, you need to go beyond whether something is statistically significant and figure out if it's practically significant. So statistically significant only says this right here, that the differences are not due to chance. It does not measure whether it's a meaningful difference in terms of practical decision making. Also, the sample size must have been very large. I want to talk briefly about this. If a sample size is large, you're much more likely to get statistical significance, because the larger the sample size, the more you are able to pick up a small, tiny result. If you have a small sample, you're not going to pick up on a small result. You can only pick up on a very large result. So if it's significant, it doesn't necessarily mean the sample size was large. It's possible to pick up a statistically significant result with a very small sample size. However, the larger your sample size, the more likely you are to get a statistically significant result. Okay, that was one of the boo-boos. I'm not sure which one that one was. Correlational study as statistically significant. With what should you be concerned? So this is kind of a stinky question. It's kind of an answer, well, of course you should be concerned with all of these things. However, when I see something that was statistically significant, but the correlation was only 0.13, which means, remember, we're worried about the r squared. So 0.13 squared gives us, 2.6% of the variance, which is very, very small. So the point is, this is not going to be a practical effect. Or if it is, it must be something like life or death situation. So certainly that is what I would want to look at in a study that I saw was statistically significant, but the effect size was very, very small. So that's the thing to look at there. Okay, another poorly worded question. Okay, I won't go into all this, but most thing here, when we're doing a table of counts, this is going to be a chi-squared. A chi-squared is when you have two categorical variables, nominal variables, and then we're just counting how many of each intersection. So if this is political party and gender, how many male Republicans, how many male independents, male Democrats, female Republicans. And then using that, we can come up with, it's a slightly different distribution. It doesn't look like the normal distribution. But all of these other distributions are based on when we have a continuous variable. So chi-squared is the test we use with two categorical variables. Even here, notice that these are typically, we could count experience in terms of a continuous variable, but we didn't. So this researcher made 3 categories, 1, 2, 3. And so because she split them into those categories, both of these variables are categorical. Okay, and that's the first 10 questions.